Hello, algebra people. Today we're going to look at section 4, graphing a function. Actually, it's called graphing a function rule, but who's counting? This is the most basic thing of graphing, and hopefully you remember how to graph points, because that's really what we're going to do today is just graph a bunch of points. Let's start off with a function rule that says y is equal to negative 2x plus 1. Now, all through math, we're going to be having to graph things for lots of different reasons. But in general, mathematicians in the real world will graph functions because they like to see what trends look like. What does this look like? If you're talking about where math is used in the real world, and I've said this before, but one of the biggest places where it's used is they make models of real world things to make predictions from. And so when we look at a function, it's for someone with a lot of experience or even maybe a little bit more experience than the average person, we could look at that and go, it's going to be a line. And I can tell some things about that line, and I'm sure a lot of you can as well. I can tell that the y-intercept occurs at 1, and this has a negative 2 as a slope, which is an indication that as x gets larger, y is getting smaller. So there's lots of things that you can kind of tell just by looking at the equation. However, we are visual creatures as human beings, and we like to see what things actually look like. So a picture is worth 1,000 words. Let's draw a picture of this function. Now later on, we're going to use just the y-intercept and the slope to graph these. But to start with, your book is just saying, you know what? For any function that you want to graph, one of the easiest ways that you can graph it, if you're starting off with not knowing what this would look like, is to just pick some values, plug them in, and create some points. And what I mean by that is let's pick some x values to plug in to this equation, and then do the math, and we'll write down what we get for y values. So let's start off and say, well, I wonder what happens if I plug in negative 1 for my x. In general, it's a good idea to plug in some negative values and some positive values just to see what happens in any particular function. If I plug in negative 1, then what's really happening is I'm taking negative 2 times negative 1 and I'm adding 1. Again, I'm just plugging in negative 1 for my x. So negative 2 times negative 1 is a positive 2. And if I add 1 more, I'm going to get 3. Let's pick 0. If I pick 0, what I'm really saying is I'm taking negative 2 times 0 and then I'm adding 1. Where is this information coming from? It's coming from right here. This says take negative 2, multiply it by the number I'm choosing for x, and then add 1. So negative 2 multiplied by 0, which I chose for x, and then add 1. Negative 2 times 0 is 0, add 1, and you get 1. Let's pick another point. 1 makes good sense. Let's choose that one. Where are these numbers coming from, Mr. Foken? Where are these x values coming from? They're coming from me. I just choose some. Choose some negative numbers, choose 0, choose some positive numbers, just to get an idea of what this might look like. So let's plug 1 in. Negative 2 times 1 this time, plus 1. Again, I'm just plugging it into this equation to see what I get for y. Negative 2 times 1 is negative 2. Add 1 more, and you get negative 1. So we get that. Let's do maybe one more. Choose a number. Choose 2. Choose 2. Okay, I'll choose 2. I plug in 2, and I get negative 2 times 2 plus 1. Negative 2 times 2 is negative 4, plus 1 is negative 3. So here's a bunch of points, right? I've got a bunch of points. In other words, each of these is an ordered pair. That's the point. Negative 1, 3, that's the point 0, 1. This is the point 1, negative 1. This is the point 2, negative 3. Grabbing my trusty straight edge. And, ooh, by the way, so I was just doing this a minute ago. Well, let me give you my little spiel on graphing. What I did here, right, as I said, I was doing this for another class, and I'm like, oh, I might as well use this again. I don't want to see you like do your hand drawn things because you think you can draw straight lines freehand. I get graphs that look like this all the time. You're like, oh, here's a y axis, and here's an x axis, and here's a point that I put on there, another point, and I drew my line, and isn't it straight? And then that looked good. No, it doesn't. If you're going to draw a graph and you don't have graph paper, then you can use your straight edge that actually has the markings on it. And I know Mr. Fokin said, yeah, in math, we don't use those markings. Well, we can if we're just going to make our own graph paper. So what I did here is I said, I'm going to line up my centimeter side, and I'll mark off every half centimeter on my lines. So I went through and I marked all those, and I marked them on this axis as well, every half centimeter. And then I labeled them this way. Even though I might not have graph paper, if I was going to plot a point, I can now see where points lie. If I was going to say, oh, let's plot the point, I don't know, 2, 4. How do you plot the point 2, 4? Well, you go over to x by 2 and then up y by 4, and you put your dot. At least we have a guide to figure out where the point 2, 4 goes. We're not just freehanding everything, right? We have a guide. So use it. And if you want to be even more careful with where you're putting your points, you could always line your ruler up here and say, I'm going to mark it off at 4 up there. See, I count up. But anyways, you can make your own graphs and be fairly accurate, even if you don't have graph paper. Now, if you have graph paper, which would be perfect, then we can make our coordinate systems to graph these. The other thing I would say is it's really weird. Like, I'll give people graph paper to make graphs, and instead of drawing the line like on the line on the paper, they'll like draw it somewhere between these lines, and that's just like ridiculous. The reason we're using graph paper is because there's a grid on there that we can use, if you know what I mean. There's our coordinate system. Again, I've made each of my axes, my x and y axis, actually fall on a line that exists on the grid. That would be step one. And then we can actually use these markings that are on here to kind of denote where the numbers lie on these axes. For example, there's the number 1 and 2 and 3 and 4 and 5 and so on. And up here, we've got the numbers 1 and 2 and 3 and 4. And I didn't do a very good job marking that one, but that's 2. And then what I do, and I started doing this a long time ago, is I will use like the opposite side. So I'm going to put, like, I wrote the numbers underneath here, but I wrote my negative numbers above the axis. So that's 1 and 2 and 3 and 4. And those are all negatives, right? And then, like, I have the numbers up here on the right-hand side, but I'm going to write the numbers down here on the left-hand side. There's 1 and 2 and 3 and 4 and such, and these are negative numbers. And the reason I do it that way is that way when I label them, none of my numbers are interfering with each other. They all kind of exist in their own quadrant, and it's kind of nice to keep things separate sometimes. Anyways, let's go ahead and plot these points that I just came up with from my table. Okay? So again, I'm going to say, let's say that you're taking a test or you're working on an assignment and you've forgotten how to graph even just a line or something, or you're given a function and you're not quite sure what it looks like. It's not hard to make a quick table like we did before. And this table is going to give us individual points that we can put on our graph. And then we just connect the dots. It's easy to graph functions, even if you have no idea what they look like. Just make a table and plot the point. So let's plot the point -1, 3. So at -1, 1, 2, 3, there's a dot. That's the point -1, 3. Okay? Because remember, everything here is going to be in terms of x, y. All right. So the first letter is your X value. The second letter is your Y value. These are not letters. These are numbers. The first number is your X value. The second number is your Y value. These are all in terms of X, Y. So there's the point, -1, 3. We're going to find the point 0, 1. Go to 0 on the X-axis and up to 1 on the Y. Boom, there's the point 0, 1. Let's plot the point 1, -1. That tells us to go over to 1 on our X-axis, and from there we'll go to -1 on the Y, or go down 1 on the Y, you might say. And finally, plot the point 2, -3. So at 2 for an X value, we're at 1, 2, 3 in the negative direction for Y, so there's a point. And once we have those points all laid out on our graph, we can grab our straight edge and connect the dots. Connect the dots, la 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 la, connect the dots, la 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 la. So here's the graph of the function -2x plus 1. Okay, so I'm going to say if you know it's linear and you know how to graph linear functions from this equation or this type of equation or any type of equation, as long as you're making an accurate graph, I don't care. If you're not quite sure, go ahead and make a table. Tables are easy enough to make. Okay? Let's talk about the ideas of continuous and discrete. We have talked about this in the past, but let me just give you maybe an example. Here is I'm going to call this something like a small stock tank or something. I want you to think about different ways in which we could fill this. Let's say that we have maybe like a 5-gallon pail over here, and we don't have the luxury of having a hose or a cistern or something that we can fill from. So we're going to have to fill up our bucket and then dump it in to here. And what's going to happen to the water level? If I were to make a graph that would show the water level of the tank over time, we'll put time down here and the height of the water on this axis. Before we start at time 0, our stock tank is empty. We haven't put any water in it yet. But let's say that every minute, I have a pretty fast way of filling my bucket or something. But every minute I can dump a bucket of water in there. So the height is going to start at 0, but 1 minute later or whatever, I dump the bucket in and immediately I fill that tank to a level. I just, boom, now I've got some level of water in there, okay? So I didn't have anything in there before, but then boom, 1 minute into my timer, I dump water in there and immediately the height grows for the water level in the tank. And 1 minute after that, I dump another bucket in there, boom. And so now there's a higher height of water in the tank. And a minute later, boom, I dump in my bucket and there's a different level of water. And I can continually do this over time, and eventually, might take a while, but I might be able to fill my tank all the way up by just dumping water in. Boom. Okay, so we're just going from boom, our water level is here, dump another one in there, my water level goes up. And this is what it looks like. It's a stair step. And we're going to call this a discrete function. Okay? Now, suppose that I have a slightly different situation, and that is that I do have a hose. Okay? So I just have I have a water hose, and I can bring my water hose out and I can fill it from there, right? So I just have a hose connected to something, and I can just drop the hose in there and fill it up. What does a graph of time versus height look like in this situation? Well, before I start to fill it, there is no water in there. But over time, maybe, it just starts to fill up. And even if I'm really kind of filling at the same rate, I could look at any time. It doesn't have to be every minute. I could look at a half a minute or a quarter of a minute or whatever and check the level, and I could plot that on here. Because I'm continuously filling this, the level is continuously changing. It's different over here because, if I checked the water level at 1.5 minutes, it's still going to be the same height as it was at 1 minute when I first dumped it in. And even if I checked at 1.75 minutes, the level will not have changed. It's still going to be there. However, the same isn't true in this function. If I check it at 1.5 minutes, it's going to be at a different level than it was at 1 minute. And if I checked it at 1.75 minutes, it's going to even be at a different level because it's continually changing, and we call this a continuous function. Okay, so we've got this idea of, hey, this is discrete and this is continuous. But I want you to notice that when I was doing this, I would kind of mark some points. I was like, oh, you know what, I'll say that those are the levels at each given minute. But those same points exist on this graph. I mean, exactly the same points. If we were to look at this point, it's at 1, 1. Well, this point's at 1, 1. And if I was to look at this point, it's at 2, 2. And if I was to look at this point, it's at 2, 2. And if I was to look at this point, its coordinates are 3, 3. But so are this point. So is this point. And so all of these points are actually exactly the same on the graph. The difference is that on a discrete graph, I really can't draw a line through those points because that doesn't tell the story what's happening. I can only draw a point through there that is continuous when we have a situation where in the real world it would have been continuous. Your book gives a brief description of what's going on here, and it just says, look, a continuous graph is a graph that's unbroken. And the reason it's unbroken is because for any x value, there is a corresponding y value that we can connect with a nice continuous line or curve if need be. But in a discrete graph, there are sort of these points that exist in our data, but I really can't connect the points because that function, whatever it is in the real world, is discrete rather than continuous. And so I can't connect the dots. All right. There are times when you sort of can connect the dots and other times where you really shouldn't connect the dots because sometimes it's discrete, not continuous. All right. And so the example that they're given in your book is this idea of the weight of the cheese in ounces depends on the number of gallons of milk that you use, and that can actually maybe be a continuous function. However, once the cheese is made and he's got all of these little bricks of cheese, when he does his sales, he's not selling really like continuous things. He's selling them by the brick that he's got, or the wheels in this case. And so if they're $9 per wheel, if he sells one, he's got $9. If he sells two, he's got 18. He's not going to sell 1.75, even though I know you can go to the store and buy little chunks of cheese. But in this case, he's just selling them by the whole wheel. So when you look at this representation, it's a discrete function rather than a continuous one. So while he was making the cheese, he can get pounds of cheese or whatever. The ounces of cheese depends on how much milk he starts with or pours in. But when he's selling it, he's selling Boom, he sold a wheel. Boom, he sold another wheel. We're not looking at a continuous piece here. So there's that. And like I said before, if you know that if you've got it down how you can graph linear functions and you've got the function there, just feel free to go ahead and graph. You don't necessarily have to make a table. But for those of us who might not be sure how to graph lines or any other function, we can make a table. And even though you might not know how to graph certain things, like y is equal to the absolute value of x minus 4, we could graph this function just by making a table. Suppose I don't know what this looks like. I have no idea if I were to graph this, what it would look like. That's okay, because we can make a table and plot the points. Now, in the world of mathematics, it's often talked about things are often talked about as being abstract. And the study of mathematics, pure mathematics, is abstract. That means that there's not a lot of practical application in what you're currently doing. That doesn't mean that it's never practical or that it can't be used, but there's a lot of studies in mathematics that are strictly abstract. And so there's this weird division between like, oh, this function here, negative 2x plus 1, in the abstract is always going to be continuous. Now, that doesn't mean that there isn't a situation in the real world that could be modeled by negative 2x plus 1 that's discrete. It just means that we don't typically consider it in math, and we're going to go ahead and make it a continuous function because we're just talking about the abstract. So as long as we're living in the abstract, we're going to connect our dots. That's all I'm saying. If we don't know what this looks like, we can make a graph just by making a quick t-table. And again, I'm going to say, let's choose easy values, but also we want to choose some things that are negative and some things that are positive in most of these because we don't know what it's going to look like. So I'm going to say, let's start off with something like negative 2. I'm plugging in negative 2 for my x, and these bars mean absolute value. And remember what absolute value stands for. It stands for the distance a number is from 0 on the number line. So if I said, what's the absolute value of negative 2, you got to think about a number line, and negative 2 is 2 units away from 0. What does that mean, Mr. Fokin? You're talking French. And I'm Italian. On a number line, like if there's the number 0 and there's the number negative 2, how far away from 0 is negative 2? Well, it's 2 units away because starting here you can go 1 unit away, 2 units away. So the number negative 2 is 2 spots or 2 units away from 0. That's what I'm talking about. So if I were to plug negative 2 into this absolute value symbol, what's the absolute value of negative 2? 2. It's the distance from 0, 2 units from 0. And 2 minus 4 is negative 2. Excuse me. Let's move on. Let's choose negative 1. That's like asking the question, at least when I say what's the absolute value of negative 1, you're saying, well, how far is negative 1 from 0? It's 1 unit away. So that's a 1. 1 minus 4 is negative 3. Let's choose 0 because it's a nice number to use. The absolute value of 0 is 0. That makes sense because 0 is 0 units from 0. But 0 minus 4 is negative 4. And then we can say, I wonder what the absolute value of 1 is. And that's 1. 1 minus 4 is negative 3. We can plug in 2. 2 minus 4, because the absolute value of 2 is 2. And 2 minus 4 is negative 2. I think we kind of have maybe enough numbers right there. Let's plot these points and see what we get. So I'm going to plot the point, negative 2, negative 2. So negative 2, negative 2. That's this point. This is the point negative 1, negative 3. So I'm going to go negative 1 and negative 1, 2, 3. I'm going to plot the point 0, negative 4. 0, negative 4 lives here. Then I'm going to plot the point 1, negative 3. 1, negative 3 is here. And plot the point 2, negative 2. 2, negative 2 is here. Because we're looking at this as a continuous function, I'm just going to connect some dots here. It looks like there's actually two different branches to this. There's a left branch that goes that way, and there's a right branch that goes this way. And so if we put those together, we have a V, which really is what an absolute value function graphs like. It looks like a V, which I always thought was ironic because absolute value starts with a V. I'm not talking about absolute, I'm talking about value. Value starts with a V, and absolute value graphs are V's. So that's what that graph looks like. And I'm not going to do the other one that's in your book as an example, but the function that they're trying to graph is x squared plus 1. Y is equal to x squared plus 1. So they're like, ignore this middle part. That's just their calculation. So they're choosing numbers, and again, choose some negative numbers, choose some positive numbers, and choose 0 as well. If you plug in negative 2 and do the math, you get 5. So the point negative 2, 5 is on that graph. If you choose negative 1 and do the math, you get 2. So the point negative 1, 2 is on the graph. So on and so forth. Plot all those points and connect the dots. And they don't have to be straight lines. In this case, when you plot this, it becomes a fairly recognizable figure that's called a parabola. It's kind of U-shaped. But even though you don't know how to graph one of these by yourself, like in y equals mx plus b form kind of idea, if you don't know what that looks like, you can always make a table of values, plot the points, and connect them. And that's what the graph looks like for that function. Okay? So that's a powerful tool. As long as we can make a table, we can graph pretty much any function that you can write up in mathematics. So that's what you're going to be doing today, is just graphing some of these things. If you know it's going to be a line, like for example, you might look at that and go, oh, it crosses at negative 3 and has a slope of 1, and I can graph that. If you don't know, make a table, plot the points, connect them, make a graph. Okay? So that's what we're doing today. Good luck to you. Hopefully you're having a good week, and hopefully we'll talk to you soon. Bye-bye.